All right, so I'm going to talk a little bit about what NLR has been looking at as far as 40 and 100 gig and what the situation, what we should expect going forwards. First, let's start out with maybe a quick review of the NLR network, the layer 1 optical infrastructure. You're probably pretty familiar with it. You've seen lots of these slides. This shows in blue, if it came out, that's the recently, about a year ago now already, upgraded. We called the phase 1, we could call it phase 3 now, I guess, infrastructure, which is built on Cisco 15454 platform with ROADMs and ROADMs and Raman amplification in many locations. The black lines are the phase 2 deployment, which is also 15454 platform. It's the 32 channel system. The phase 3 is a 40 channel system, and the phase 2 was mostly pre-ROADMs. The dots indicate, the blue dots indicate regeneration points around the network, or forced regeneration points around the network. You can see that with the phase 3 deployment, we were able to achieve much longer distances without regeneration. For example, Los Angeles to Seattle is our longest distance without regeneration, which is, I believe, over 2,200 kilometers. And in other areas, we were able to achieve very long distances as well without regeneration. One of the requirements of moving forward to 40 and 100 gig is to try to maintain those distances as much as possible. Another review is the fiber that Glenn mentioned earlier that NLR is running on top of is relatively new fiber. It's low dispersion E-leaf fiber, and that's going to come into play when we talk about 40 and 100 gig. The core optics, 1544 core optics, were optimized for the 10 gig lambdas that are going across it right now. The typical 10 gig signal, non-return zero. It's one of the main benefits of that core optical system, is an analog optical system, is that it will support these higher speeds with very little changes to the core infrastructure. Because it's analog, you can basically pump many other signals into it, and it's just passing light for the most part. Now, there's obviously caveats to that. And I believe I covered, so unregenerated distances. So the West Coast, 2,164 kilometers unregenerated. And phase 2, we're doing distances of 1,000 kilometers or less unregenerated. One of the other benefits is that we're capable of expanding both of those up to 80 channels at 50 gigahertz spacing in the future. So as Grover said, the life expectancy of our core optical system is a very long time frame. I believe I put in here somewhere 10 plus years. I believe Grover stated earlier 15 to 20 years. He thinks that the core optical system will be able to continue to support National LambdaRail. So what are the benefits of going to 40 or 100 gig? We're talking about going to 40 or 100 gig wavelengths, not 4 or 10 wavelengths at 10 gig each. And that hasn't been done a whole lot yet in the R&E space. Having the ability to do a 40 gig lambda allows us to solve the large flow problem, which us in the R&E community frequently talk about. We can also go expand our 10 gig capacity that we have right now. So using 40 or 100 gig muxponders in the future, we can put up to 320 10 gig circuits and up to with 40 gig muxponders and up to 810 gig circuits with 100 gig mux ponders on the existing core infrastructure. Obviously, there will probably end up being a mix of actual 40 or 100 gig lambdas versus lambdas that are mux ponding 10 gig circuits. Another benefit is that we expect to reduce the space and power footprint, which is a constant problem being in a provider facility like Level 3. So going to 40 and 100 gig presents a lot of challenges in the optical domain. Basically taking the typical 10 gig NRZ signal and trying to boost it up to provide 40 or 100 gig is not going to scale. There's lots of problems here. Bandwidth of the signal getting too wide, your optical signal to noise ratio and tolerances get incredibly small, and tolerance to factors on the fiber like PMD. I'm not going to go into these in any detail, just show you there's a huge list. So here's an example. A 40 gig NRZ signal gets extremely wide, and so it would tend to overrun adjacent signals, and you can see crosstalk between adjacent signals causing bit errors and things like that. So it's just an example of how much wider a signal like that would be. So what is the solution to that? Providers, all the hardware providers have been looking at modulation schemes. So those of you who've been around a long time and have used modems in the past and are familiar with the ways that they used modems to get higher speeds out of your two copper wires from the phone company. This is basically the same types of technologies. So many different modulation schemes. Again, not going to go into this in much detail, but you can put closely spaced signals together. You can modulate by amplitude, modulate by phase. Many different flavors of phase and polarization modulation schemes. Here's an example of some different modulation schemes, and some of the factors that you have to think about is the width of these modulation schemes. Here, the black arch is a 50 gigahertz filter, a representation of a 50 gigahertz filter, and these are different modulation schemes, and indicates how well they fit within that 50 gigahertz filter. So there's lots of different things to think about when trying to choose a modulation scheme. We actually did some testing on the West Coast of several vendors sending their 40 gig signals across the NLR infrastructure. And here's an actual representation, the measured representation of some of those signals. You see the sharp, narrow spikes are the 10 gig signals that are in production on the network, and you see three that are obviously different that are 40 gig signals from various vendors. I won't tell you who's who, since I'm not sure I'd be allowed to, but you have the sixth one over has basically four 10 gig signals that are closely spaced together up to 40 gigahertz and 40 gigabits. And you'll notice that it's a very wide signal, and it's actually interfering with the 10 gig signal next to it, or vice versa. The 10 gig signal is interfering with the 40 gig signal. The next one over, I believe, is ADPSK, and it's a different modulation scheme, and it's a little narrower, a little better at fitting that 40 gig signal in. And then the next one over is two 20 gig signals that are using some form of modulation to create two 20 gig signals that are next to each other. So the winners in this modulation contest, they vary greatly per vendor, as you could see, in the short and medium distances primarily. When you start getting into long haul distances, it pretty much comes down to some flavor of PM QPSK, which is primarily polymux quad phase phase shift key modulation.